Okay, we have a Coke versus Pepsi for Bertrand price competition. And both their products are horizontally differentiated because obviously one is not absolutely better than the other. That would be vertically differentiated. There is some preference between customers here, so it's horizontal. Some might argue that Coke is absolutely better than Pepsi, but yeah. So we'll get this done. So focusing on the left hand side, so I'll write that up here. Price multiplied through by its price minus its marginal cost. And so you will distribute. Start down here. Distribute, take the partial derivative or differentiate it, find the slope, set it equal to 0. That is where its profits will be maximized. This slope, well, it will end up being I think it's a parabola. Not sure if it's upward facing or downward facing. Either way, we'll get 63.42 P1 minus 3.98 P1 squared plus 2.25 P1 P2 plus 314.56. That is a minus, sorry. Plus I'll just keep it in terms of 2 decimal places. P1. And lastly, you have a negative 11 P2. And look for any like terms. I see a like term there, I see a like term there. Taking the partial derivative with respect to P1, you get 83.16 minus P1 plus 2.25 P2, setting that equal to 0 and solving. You get get 10.44 plus 0.282. And now you have a reaction function for P1. So the price will be determined by what P2 is. It's in terms of P2, so it's a function. And we'll come over here and solve through. And it's good because these are different. Their marginal costs are different, their cost structure is different, their demand function is different. So you get something different and then you have to set them, substitute one into the other, system of linear equations, substituting in, solving, you get their prices. Going to be different, going to take on the qualities of what an actual market would look like when you're doing these type of equations. Because this was derived from statistical data that got the demand curve for both Coke and Pepsi. I think it was done in like 1992. So they're using data from maybe the 80s. And surprisingly close. Like 30 cents off or something like that in terms of their prices they ended up with. Anyway, solving for this, let's try and see if I can keep this. So I have that much room to solve it. $196.09. P1. And combining like terms, we have that and that, so that's plus. $71 point. Taking the partial derivative with respect to P2. We'll get 71.22 minus 10.96 P2. And the other terms are not there, setting that equal to 0. 6.49 plus 0.127. Add a 7 on there for good luck. And you have your best reaction function. And chuck in a P1 on the end of that so that you can solve it. And going back over here, I'll finish it off. So 6.49 plus 0.1277 P1. So now we substitute 0.282. That is being multiplied through, so substituting in, got 6.49. Might be a bit too late to point out that this price for 1, when they're substituting it in, when it's the best guess. So in this demand equation, the P2, like price 2, when firm 1 is setting their price, is going to have a best guess about what that price is going to be, because they can't be communication. There's laws against monopolies and, well, duopolies and oligopolies communicating. Not so much monopolies, they're just one firm with everything. And then you're solving this through. So don't add these. So don't add these first. You want to distribute, I'm saying it's doing it 3 times. You just want to distribute it across those terms first, that coefficient outside the parentheses. And I'm going to stop writing P1 in terms of P2, even though I think that is the correct function. Plus, so 0.282 plus 1.83. I'll just do it in terms of 2 decimals. 0.82 times 0.1277. That is our okay, just broke my rule there. P1. Solving through for P1. P1. Do it up here. P1 minus 0.036 P1 equals the sum of that, which is 10.44 plus 1.83, 12.27. We'd have 0.964 P1. P1 is going to be equal to 12.728. Or we'll round it up to 12.3. No, we won't. 7 cents. That is your price for firm one. That's what they're going to set. Coming over, doing the exact same thing here. Again, don't add those. You want to multiply them through and then add. So 1277. $1.33. 0.036. So you have P2 minus 7.82. You're going to get and that's your price for number 2, firm 2. Thanks for watching this solve. If you wanted to get the quantity and profit, you would just plug your prices into your quantity function or demand function, and you would get your quantity. Profit, you'd have to multiply your quantity through by the marginal cost, and do the price times quantity minus total costs. So you'll have your quantity, price, and profits at the respective quantity and price. Now, last thing before we go, show you a quick graph of what we're doing here. Should always label your graphs, but I'm not going to. Well, I'll label them P1, yeah, okay, P1, P2, Coke and Pepsi. So, Coke, stuff $10.44, and, oh, come on, $6.49 for Pepsi. I think that's the lowest they can charge. And then your respective prices that you got, $12.72 and $8.11. So I'll just do it up here. $8.11. And you'll have your respective lines. And there you go. So these are upward sloping because of how the response functions look. You have a positive there, which means you have that is going to be your intercept on the x-axis for, well, that's P2, sorry. So on the x-axis for Coke, because they're on the x-axis, you put $10.44, which is, you go out $10, and that's the only way they're constant. And then same thing for y on the y-axis. So these could be, so P1 could be PX, P2 could be PY. And that will make sense. And you put their respective prices that they're going to charge. The intercept point where those two lines intersect is your equilibrium. That's the best response function for what they're charging. And you can move up or down those lines. So profit maximizing price for any price charged by firm 2 will be along this reaction function. That's going to maximize their profits on that, and that's going to maximize their profits given the market. And that is your work. Not too hard. And a real life example. So practical applications. That's what you want.